Evaluating the limit of a piecewise function, you want to pay attention to this side over here. This tells you what's happening to the right of 4 and to the left of 4. And that's what we care about when we're evaluating limits, is what happens to the right and what happens to the left. So they want us to find the limit at 4, and that is where this piecewise function is split into two pieces. So if we want to evaluate the left-hand limit of 4, we would look where x is less than 4 and plug in 4. So 8 minus 2 times 4 is going to give me 0. So the limit on the left side is 0. If we look at 4 on the right side, so up here where x is greater than 4, we plug in 4 to this piece, and we get square root of 4 minus 4, which is also 0. So that is telling me that the left is 0, the right is 0, so the overall limit must be 0. If you were to graph these two pieces, you would see a graph like this. And we can see the left side is a line going down towards 0 at 4, and the right side is a curve going down towards 0 at 4. So that is why the limit is 0. Both sides approach the same y value. The greatest integer function is this double bracket symbol on the x, and whatever your x equals inside, the value of the function is the largest integer that is less than or equal to that value. So for example, 4 is an integer, so 4 is the answer. 4.8 is not an integer, so you want to go to the largest integer that is less than this, which would be the 4. Pi is not an integer, it's 3.14, so you want to go down to 3. Square root 2 is about 1.4, so you go down to 1. Negative 1/2 is not an integer, so you go down to negative 1. So they want to know, what is the value of the limit as x approaches 3? Well, let's consider a graph of that. If you look at this graph, here we go, at 3, you would see that the left side of 3 is staying at 2. It's going to 2. Up here, the right side, imagine there's a line right here, the right side is going to 3. And so here we're seeing that the left side and the right side do not agree, so the limit does not exist at 3. The squeeze theorem. So if f of x is less than or equal to g of x, which is less than or equal to h of x when x is near a, except possibly at a, and the limit at a for f, which is this one, equals the limit at a for h, which is this one, if those are equal, then the limit of g at a must also be the same as the limit of f and h at a. So here is a graphical representation of that. If the limit of f, which is the blue, and the limit of h, which is the yellow, are both L at a, and g is between those two functions, then g must also have the same limit as h and f. So if the top is the same, the bottom is the same, whatever is between them must be the same, because it is squeezed between them. So in this example, we don't even know what f of x is, so I can't just plug 4 into f and get my answer. But we do see that this function f is squeezed between the function 4x minus 9 and another function x squared minus 4x plus 7. So what we have to do is plug in 4 to the bottom function and the top function and see if they're the same, then that is the same as the function squeezed between them. So if I plug in 4 here, I get 16 minus 9, which is 7. And if I plug in 4 here, I get 16 minus 16 plus 7, which is also 7. So if you plug in 4, the bottom function is 7, the top function is 7. If f is squeezed between those, f must also have a limit of 7. So that's the answer. So what about the limit as x approaches 0 of x squared times sine of 1 over x? Well, that is a really complicated function that we don't know how to graph by hand. What we're saying is we know the answer is 0, so show why it's 0. This graph right here has squeezed this odd function between the curves x squared and negative x squared. So the pink curve fits between two functions that we do know. We do know these parabolas. And we know that at 0, the limit of this top parabola is 0. we know the limit of this bottom parabola is 0 at 0. And if the pink function, this crazy sine wave, is squeezed between them, then it must also have a limit of 0 at 0. So that's using a graph, but let's use algebra. What do we know about this function as a whole? Nothing. But what do we know about sine? We know that sine has a range of 1 to -1, or -1 to 1. So sine has a range of -1 to 1, because we know the graph of sine. It goes down 1, up 1. Well, what if it's a 1 over x inside? It doesn't matter what sine has inside for its argument. It still has a range of -1 to 1. So we can change our sine to 1 over x. It still has a range of -1 to 1. So I'm trying to take what we know and transform it into what we don't know. Well, what about x squared? So let's just multiply everything by x squared. So I'm going to get -x squared sine 1 over x, and x squared. Well, now I've just created a function that we want to know something about, but we didn't know anything about previously. And I just so happen to squeeze it between the functions -x squared and +x squared. So if I want to find my limit at 0, I can look to the left and I can look to the right. If I look to the left, which would be this one, I get -0 squared, which is 0. If I look to the right, which is this one, I get 0 squared, which is 0. And because this function is squeezed between those by squeeze theorem, the limit at 0 of the in-between function is also 0.